Guys, give me just a minute. I'm getting some stuff kind of set up in the background. Okay. Okay. I got a new document camera, so I'm trying it out, seeing how it kind of works until it's a little different than the one before. Let's see if I can get the focus right. A little bit. Okay. So today we're going to be talking about, where am I? We're going to be talking about polynomials, actually. And if I was going to write the book, I would have started with this section. Your book really does 3.1, which is about a very specific polynomial, the quadratic polynomial, before it jumps into the broader definition of polynomials. So really, this should be written as polynomial functions. That's a better title for this section, polynomial functions. So before we really jump into the fun stuff, we've got to define what a polynomial function is. Now, I'm going to try to write with this pen and see how it picks up on your side. Let me know if it's, gosh, I just need to be a little bit higher. Let me know if it's not thick enough, if you can't see it, okay? There we go. Okay, that's not too bad. Okay, so we've got to define what a polynomial is. Well, a basic polynomial is written really with single terms descending. Now, it might have missing terms, but let's look at an example first. So if we have like f of x equals 2x squared minus 3x plus 1. Okay, yeah, I don't like I want it to be thicker than that. Okay, I'm going to use the real ones. This would be a good example of polynomial. This is a quadratic polynomial that we talked about yesterday. Now, to make something kind of fit the definition of a polynomial, each x value has to be raised to an integer exponent. So we've got 2, here we have 1, and really this constant over here, it's raised to x to the 0. We just don't write it, okay? So each x value is raised to an integer exponent, and each coefficient is a real number. Okay, it's a real number. 2, -3, and 1, they're all real numbers. So if we looked at something like, let's say g of x equals -3x to the 4th minus 2x cubed plus x minus 5, something like this. This would be another good example of a polynomial. Each exponent is raised to a power. This is really to the 1 power, right? And this is a constant. Again, the constant's really raised to the 0 power, but anything raised to the 0 is just 1, so we don't write it. So this would be a good example of a polynomial. Now the coefficients are right here, right? This was a 1 coefficient, and that's really a -5 constant, but it's also considered a coefficient. Okay. Something that wouldn't be a polynomial. Let's say we had z of x equals -2x to the -3 minus 4x squared plus 7. Okay, this wouldn't be considered a polynomial because this first term's exponent is negative. Okay, cannot have negative exponents in polynomials, not happening. So polynomial here, not a polynomial here. Let's do another one that's not a polynomial. Let's say we had like h of x equals 4 square root of x minus 2x to the 4th minus 8. Okay, let's keep going with this one. 8x plus 1/2. This would not be considered a polynomial because of the square root of x. Really, the square root of x, if you remember, the square root of x can be written as x to the 1/2, right? So because of that, we would never see a radical. We never see a square root of one of the variables in a polynomial. So this couldn't be a polynomial because really we're raising that x value to a fractional exponent. But all the exponents have to have an integer exponent. All the x's, I should say, have to have an integer exponent, like 4, 3, 1, 2, 8, 9, whatever. Okay, so this would not be a polynomial as well, and we won't focus too much on that. I mean, the majority of what we're going to see today and moving forward over the next 3 sections, they're going to be polynomials. We just have to kind of dig information out of this polynomial. Okay. So let's talk about how polynomials can be written, and then we're going to kind of find some stuff about that. Polynomials can be written 2 different ways. First is factored form. And I want to show you the connection here between factored and kind of the traditional form of a polynomial. Let's say we had 2x times x minus 3 times x plus 2. Okay? This would be considered a factored form of a polynomial function. If we FOIL this out, we'll get it into what we traditionally see with a function or with a polynomial. So if I want to multiply this out, so I'm going to FOIL these two together. F of x equals 2x times x squared plus 2x minus 3x minus 6, okay? So f of x equals 2x. I can add the middle 2 terms, so x squared, this is minus x minus 6. And then I've got to distribute the 2x. And I wind up with f of x equals 2x cubed minus 2x squared minus 12x, okay? So both of these here and here are the same exact function, okay? And it's a polynomial function. If you look at it this way, we can see we've got a 3rd degree here, 2nd degree here. Really, there's a 1st degree here, right? We don't write it. 1st degree here term. So, but they're written 2 different ways. And we can pull the same information out that we need for this first part of the polynomial section in either way, but we pull it out in different ways if it's written in these 2 different forms. So I call this one factored form. And you'll hear me say factored form of a polynomial. That's what I'm talking about. Notice we have 3 factors here, right? 2x. And when I say a factor, it has to include an x, okay? So we've got 2x, we've got x minus 3 and x plus 2. And this is, I'm just going to call it traditional form. I don't think it necessarily has a name, but this is the traditional form that you see polynomials written in. And then from yesterday, you know, that general form of the quadratic, it was written in this traditional form. Now, the standard form of the quadratic is not factored because it had like a constant at the end. That's something different, okay? But we've got factored form and we have traditional form. Okay, and they both link together. And I want to show you that too, because what we're about to do, we have to pull out what I call the leading term. It's going to tell us a lot about the polynomial, really the graph of the polynomial. The leading term for this example is right here, 2x cubed, okay? That's the leading term. The leading term is always the term with the highest degree, okay? The highest degree right there is 3. And the leading term tells us 2 things. It tells us the leading coefficient, which for us is 2. And it tells us the degree of the polynomial, which for us is 3. It's right there, okay? And these 2 things are going to tell us about the graph of polynomials, which we'll get to in a minute, but I got to go over how to find it first, okay? Now, if you have something in factored form and you're asked about the leading coefficient and degree, if you need to pull it out, what you can do is actually multiply all the degree terms from each factor. So to do this, you would actually multiply, this is kind of its own degree out here, the x plus 2x. Then you would multiply the x here. You wouldn't worry about the minus 3 and multiply the x here. So 2x times x times x. And you'll see the leading term is going to be the exact same. 2x times x is 2x cubed. Okay, so these of course, would have the same leading term. They're the same two functions. Okay, and this will tell us something here in a minute, and we'll get to that. Okay, but I need to really explain degree and leading term. Degree tells us a lot as well. Okay, degree is going to tell us a lot. Okay, let's do another one of these, kind of get this kind of hemmed up. So if we had a function g of x, and it was written in that traditional form, let's say negative 3x squared plus 2x to the 5th minus x plus 4, okay? Minus 3x squared plus 2x to the 5th minus x plus 4. And all I'm going to do is ask you for the leading term, and then the leading coefficient, and the degree. Okay? Well, for this one, the leading term is always the term with the highest degreed value. It's right there. This is not written in descending order, right? We have to write it in descending order moving forward to do other fun stuff with it. But for now, I'm not worried about putting it in descending order. I just want to pull out the leading term. So the leading term is right here, 2x to the 5th. That means my leading coefficient is 2, right? So it's the number in front. And my degree is 5, okay? Questions about that? It's pretty sure this is more of a descriptive thing, right? Being able to visually see it. So let's look at one that's in factor form. Let's say I had negative 2, 2x plus 1, x minus 3 squared, okay? This would be in factored form. And I'm going to ask you the same thing. I'm going to say, okay, what's the leading term? What's the leading coefficient? And what's the degree? Okay, so leading term, leading coefficient. Now, in my brain, I need to think of it as x minus 3 multiplied out twice. And I'll show you, it kind of helps us. But realize, if we've got a binomial squared, what this really means is we have negative 2 times 2x plus 1 times x minus 3 times x minus 3, right? If we were going to write it out. Okay? And then to get the leading term, you'd multiply, if we have any kind of coefficient out here, like negative 2, the previous one we had 2x. We're going to multiply that times each of the degree terms inside the polynomials. So negative 2 times 2x times x times x. So you would get negative 4, negative 2 times 2, and then we've got 3 x's, so x cubed, okay? The coefficient, leading coefficient will be negative 4, and then the degree is going to be 3, okay? The degree is going to be 3. Now I want you to notice something, because this is going to be important coming up. The degree will always match the number of factors with an x. Notice we have 3 factors that contain an x value. Therefore, our degree is going to be 3. Like if we go back to the previous example, when we're in factored form up here, we have 3 factors that contain an x, 2x, x minus 3, and x plus 2. And our degree wound up being 3. That's not a coincidence, okay? Your degree and number of factors with an x will be the same, okay? They'll be the same. Okay, So let's look at why this matters, and we'll keep doing examples of that as we go along. Let's look and see why this matters. What does it tell us? It actually tells us the end behavior of these polynomials, okay? Because polynomials wind up always being smooth and continuous, okay? Like, I don't know what the equation for this graph is, something that looks like that. I don't know what the equation looks like, but I can tell you this is a graph of a polynomial equation. It's smooth. There's no corners like that, like the absolute value graph. The absolute value had a corner, right? There's no corners. There's no crazy what's the word? We're gonna get to it in a few sections. Asymptotes. There's no asymptotes. It doesn't make some steep line here. There's no jumps. Look, it's gonna go. Polynomials will always have a domain of all real numbers. Remember in the quadratic how the domain was all real numbers? It's because it's continuous. It goes forever to the left and forever to the right, okay? So polynomials are always smooth and continuous. Always smooth and continuous. So what the degree term tells us, though, is what's happening at the end of this polynomial. What's happening all the way to the left and all the way to the right, because it either has to go up forever or down forever. Same thing on the other side. It's got to go up forever or down forever eventually. Now, it might make a few, humps along the way, but it's going to go up forever or down forever, and the same thing for the left and the right. And the leading degree actually tells us that. So the rule is actually on page 350, but I'm going to kind of go over it with examples. So let's look at this first example. We've got f of x equals, let's say, 3. Now I'm going to write these in descending order so we can easily spot the leading coefficient. Let's say 3x to the 4th minus 2x plus 1, okay? 3x to the 4th minus 2x plus 1. So the leading term, I'm going to call it LT because I'm sick of writing it out, is 3x to the 4th. But what matters is the leading coefficient is 3. And for us, what matters is that it's positive. We've got a positive leading coefficient. And our degree is 4. Now what matters for us is that it's even. We've got a positive leading coefficient, and we have an even degree. And what happens when we have a positive leading coefficient and even degree, the end behavior at the end to the right, it's always going to go up, and to the left, it's always going to go up. Now, something happens in between. I'm going to just draw dotted lines. I don't know what happens in between. But the end behavior to the left, it's going to go up, and to the right, it's going to go up. Now, the way we write that in behavior would be like this, okay? Up and up. To the left, it rises, and to the right, it rises, okay? To the left, it rises, and the right, it rises. Now, we know this already, right? I mean, the quadratic section we just did, if a, which this isn't a quadratic, it's x to the 4th, but remember, if a was positive and it was a quadratic, that's an even degree. It was up and up. So the next one we'll do, I'll do one that we know, okay? So the next example would be, well, what if we have a negative? Well, we know it just flips. So let's do one like this. Let's say we have g of x, and I'm going to make an even degree polynomial, but negative. So let's say we had negative 2x plus 1 and x plus 3, okay? Now look, I know this is a second degree polynomial because we've got two terms, two factors that contain an x. But I'm going to find the leading term just to pull out the leading coefficient and the official kind of degree. So the leading coefficient, look, I got it. That's really -1. I have to multiply the -1, the 2x, and the x. So the leading term would be -2x squared. So that means the leading coefficient's -2. So for us, what matters is it's negative. And then the degree, though, is 2. So for what matters for us, actually, is that it's even. Okay, what matters for us is it's even. So I don't know actually what this graph, like, what the vertex is. You're more than welcome to find it if you're going to FOIL it out and find it. But what I do know is because we have really a quadratic and even, and that a value is going to be negative, right? I know that this goes down and down. Now, we know it's going to go up somewhere and then it's going to come back down. I don't know where because I don't feel like finding the vertex. But for now, that's what this means, okay? So the end behavior for this one's going to be down and down. So look, if we have, and if you want to write this down, that's fine. But if we have an even, degree here, we know we're going to come where we came from, okay? We're going to leave where we came from. That's a good way to think of it. If it's even, it's going to be the same, either up and up or down and down. Now, the leading coefficient tells us if we're up and up, positive up and up, or if we're down. The leading coefficient, if it's negative, it's going to be down, okay? Odd degree is actually going to be opposite. So we'll do an example like that now. So if we have an odd degree, let's say we have h of x equals 2x to the fourth minus or plus 5x to the fifth minus 2x plus 3. Okay. Now I'm going to write this in descending order because you need to understand that that's not the leading term here. The leading term is really 5x to the fifth. Then it would be 2x to the fourth. Now there's no cube term. You can write this in descending order with missing terms. There's nothing wrong with that. And we're actually going to see that, I think, in the next section. Is it the next section? Yeah, it's the next section. We're going to talk a little bit about this. So if you want to write this with missing terms, look, there's no cube term. There's no squared term. But we have an x and a constant, okay? This would be this h of x polynomial. This h of x polynomial would be written in descending order, right? 5, 4, 3, 2, 1, 0, descending order with missing terms. So we've included the missing terms. But for us, we want to know what the leading term is. Oh, it's 5x to the fifth. That means my leading coefficient's 5. It's positive, so I'm going to put a little positive sign there. And then my degree is 5. It's odd, right? Now, what this means is my end behavior is going to be opposite. But I'll tell you, if you have a positive leading coefficient, you will always end up and to the right, okay? Positive leading coefficients, like the very first example we went over, positive leading coefficients always end up and to the right, okay? So positive leading coefficients always end up and to the right. The opposite means that we're going to end down on the other side. So the left-hand side means we're going to go down. And it does something, okay? We'll go over the middle stuff. That's really what the next 3 sections are over, okay? That's what the end of this section and the next 3 sections are going to be over. Okay, so that means our end behavior here, to the left, we're going down. To the right, we're going up. It's got to be opposite because the degree is odd. And because the leading coefficient is positive, it's got to go up and to the right. Okay, so that means the other side is down and to the left. Okay, I'll let you ask some questions. Let me get through this last example here. We'll do another one where you have to FOIL it out to really see what's going on. Let's say we had g of x, and we've got, let's say, negative 2x times 3x minus 5, x plus 1, and x minus 2, 1, 2, 3, 4. Let's say x minus 2 squared, okay? So you've got this polynomial. It's in factored form. I can tell you the degree, right? I mean, really all we need to know is the degree and the leading coefficient. I mean, I'm going to do the whole rigmarole again, but you don't, I mean, you kind of see the intuition here, or intuitively kind of see it, that's fine. But look, the degree, we've got an x here, we've got one here, here, and really we have this one twice, right? Because it's squared. So 1, 2, 3, 4, 5. My degree is going to be 5 because really I have 5 factors that include an x. Now, I'm not going to write this one out twice again like I did earlier. I'm just going to leave it there. Now my leading term though is going to be negative 2 times 3. So that's -6. And then x times x times x times x times x, right? So x to the 5th. So that means my leading coefficient, -6, it's negative. That's what matters for us. My degree is 5. Again, that's odd, right? So what this tells me, because we have a negative leading coefficient, we're going to end up to the right going down. To the left, though, we're going to be going up because it's opposite, odd opposite. And then something happens in between. We have something like that. So the end behavior is actually going to be up and to the left, rises to the left, falls to the right. Okay? Rises to the left and falls to the right. And I'm going to kind of pause it here. And I'm going to give you a few examples. And all I'm going to ask you for is the end behavior. But are there any questions before I just kind of give you a few examples to see if you're kind of getting it? I don't mind going over anything. Okay, I'm going to give you a few examples, and all I want you to tell me is the end behavior. Remember, it comes from the leading term. So let's say we've got a of x equals 4 minus x squared plus 3x. B of x equals 2x to the 5th minus 8x plus 1. C of x equals 3x minus 4, x plus 1 cubed. And then let's say d of x equals 4x minus 1 to the, let's say to the 3rd power. Why not? Okay. I want you to try those 3. Try those 4. I'll give you a few minutes. And all I want you to tell me is the end behavior. I'm asking the end behavior on all 4 of these, okay? Just give me the end behavior on all 4 of these. Okay, let's see here. So this, keep going if you're working. I know these are going to take a little bit to kind of think through. This first one, though, the leading term is actually negative x squared, right? So that means my leading coefficient's negative. It's -1, right? And then my degree is 2. So that means my end behavior, because it's even, I know it's going to be the same, up and up, down and down. But because it's a negative leading coefficient, it's going to be down and down. So that would be my end behavior for this first one. The second one, we've got an odd degree. The leading coefficient, I'm just going to underline the leading term. Leading coefficient is positive, right? The degree is odd. So it's got to be opposite. Now it's positive leading coefficient. So I know this is going to go up and to the right. It's an odd degree. So I know it has to go down the other way. Okay. It's got to go down.
So you don't have to multiply the numbers when you're getting your number of x's.
I'm not. Are you talking about for this one?
Both of them.
No, neither one of these are factored, right? Like they're not in this factored form.
Uh-huh.
So we don't have to multiply anything. Really, we just have to get it from the equation itself, right?
Okay, gotcha.
Yeah, like
Okay, I see
now
what
I'm
you're
gonna have
saying.
to on these next two though. Okay.
Okay, gotcha. Yeah. I still
Okay.
came out with the right answer.
No, I got you. No, yeah. No, that was a good question. So let's look at this. Like this one, I'm gonna have to multiply by. We've
Okay,
got 3x, and then we really have 3 of these factors, right? So I'm gonna just kind of underline it 3 times. So the leading term here would actually be 3x. Now we got 1 and then 3 more of these. So 3x to the 4th, right? And I'm not writing out x plus 1 three times, but that's what's going on. So that means my leading coefficient's 3, so it's positive, right? And my degree is 4, so it's even. Even. Now, for this one, leading coefficient is positive. I end up into the right, but then it's even, so it's also up and to the left. So this would be my end behavior. I'm not sure who asked me that because it didn't pop up on my screen, but I'm hoping that's what you were talking about.
it was Chastity.
What?
It was me, Chastity.
Oh,
It was
okay.
me, Chastity. I get it. I immediately wanted to go ahead and multiply those numbers like you have to do in the factored form.
I got you.
That's all.
No, that's all good. So now this one, it's just the same factor 3 times. So I'm just going to multiply this leading term 3 times. So the leading term for the overall polynomial, well, 4 times 4 times 4 is 64. X times x times x is x cubed. So we wind up with the leading coefficient is 64, positive, but then the degree is 3. It's odd, right? Oh, so it's the same as this one. So it winds up being down and to the left and up and to the right, right? Up and to the right because it's positive, but then down and to the left because it's opposite, it's odd. Okay. And I know this isn't, I don't think this is like a ridiculously important thing per se, but we're gonna need it as we start graphing these things, and it'll pop back up. So it's gonna pop back up, and we just have to know it. And you'll see, I'll remind you of it when we get to the examples where it pops back up, but it's going to feel like we go off onto like something totally different. Really the next kind of objective from this section. But realize we need to have this in the back. So once we start graphing, look, we know how to graph quadratics, but we're going to start graphing things with like, 5th degree, 4th degree, 3rd degree. And to graph those, we have to know the end behavior of the function, okay? We have to know the end behavior of the function to graph those. Okay, hold on. Paper, hold on. Okay, we finally come to, in my opinion, probably the most important topic in college algebra, which is the zeros of the polynomial. Okay, the zeros of the polynomial. So I'm going to define this, but we kind of know what the zeros are already. If you've never heard of it before, you know it because we found it previously in this. Actually, we found them yesterday, but we just didn't call them zeros. So zeros of a polynomial, this is where f is 0. Okay, that's a very basic way of defining it. It's where f is 0. Another way to think of it is the x values, or I should say the domain values, that make f of x equal to 0. Okay, these are 2 different ways to define it. You don't have to memorize anything, but it's just the x values that make f of x equal to 0. Okay, which is kind of neat here because really all it is, and I think this is making y equal to 0, right? So to find the zeros, you find them the same exact way as finding the x-intercepts. So on a graph, they're going to look like the x-intercepts. But the issue is that zeros could be real or non-real. X-intercepts could only be real, right? Because we're only dealing with the real graph. Zeros can be complex. Oh, gosh, complex. They are complex, but can be complex. What this means is they can be real or imaginary. Okay, that's not the best way. The math people are critiquing me right now if they watch this video because all numbers are complex. But really, it means that they can be real or imaginary, where x-intercepts can only be real. So I'm going to write right here. Look, they're found the exact same as x-intercepts. They're found in the exact same way as x-intercepts. Okay, we're just going to call them zeros now, and we don't have to write them as a coordinate. They're just x equals something that creates the zero. So that's why in the last lecture in 3.1, I asked you to find the x-intercepts and the y-intercepts. The reason I found the x-intercepts is really it leads to this idea of the zeros of the polynomial. So the zeros are just where the x crosses the x-intercept, but also we could have additional zeros that are non-real that you can't see on the graph. Now, we won't get to those in 3.2. Those imaginary zeros, I believe, are in 3.4. We'll get there. For now, the book does a really good job of kind of baby feeding you the zeros of a polynomial, which is great. I'm glad it does this because it kind of presents it in a way we've already seen before, or we should have already seen before. So let's look at an example here. And I'm stealing this straight from the book. I don't think they give another example that's, well, I can find one. Yeah, I'll find one. So let's say, actually, yeah, I'm going to do one that's, f of x equals x cubed plus x squared, 3x squared minus x minus 3. Okay. X cubed plus 3x squared minus x minus 3. Now look here, I'm going to let you in on a few things we know already, right? This is a cubic function, okay? It's not a quadratic. Really easy to solve if it was a quadratic because we just could use a quadratic formula. This is a cubic function. We have to solve it differently. Leading coefficient's 1. So I know the end behavior on this thing, just to pop this in. The end behavior, it's an odd function, positive leading coefficient, so it's going to go up. Odd degree, so it's going to go down and to the left. I know the end behavior looks like this, okay? That's just reviewing what we went over. But for the next part, I'm going to ask you to solve for the zeros. Solve for the zeros. Now look, we solve the zeros the same exact way as we solve, or as we find x-intercepts. And if you remember, to find x-intercepts, we set this entire function equal to 0, right? It's the x values that make f of x equal to 0. So we have to set this entire function equal to 0. And now we got to solve it. Now look, unless you already know how to solve zeros, which some of us might know how to do, I say solve zeros, solve polynomials with a degree higher than 2. You might not remember how to do this one. Now, the first, or the book first goes over solving these by factoring. And to solve this by factoring, you would have to use factor by grouping. There's 4 terms here, right? X cubed, 3x squared, minus x and minus 3. So you'd have to solve with a factor by grouping. And if you don't remember how to solve by factor by grouping, get on the YouTubes and look it up. But I'll go over it kind of slow just to kind of jog your memory a little bit. Factor by grouping, you had to have 4 terms. You group the first 2 together, and you group the second 2 together. Okay? Then you factor out the GCF of the first group. This would be, I think, just x squared, right? That leaves you with x plus 3. And then you've got to match these 2 groups. So to match these 2, I would need to factor out a -1. You see how it matches the x plus 3? These 2 match, okay? And if they match, I could factor out the x plus 3. Now I'm going to continue this up here, guys. I could factor out the x plus 3, and it leaves me with x squared minus 1, right? The leading coefficients. Ooh, and these popping. Okay. Now look, we have to, so we just did factor by grouping. We took all addition and subtraction and we made it into two things that are being multiplied together, which is great. I'm going to continue this though, because this polynomial factors as well. It's a difference of squares. X squared minus 1 is x minus 1, x plus 1. Okay. If you're coming from intermediate algebra, these are two topics that were straight out of intermediate algebra, right? Factor by grouping is in there, and so is difference of squares.
Totally remember that.
Good. Awesome. Hope that's not sarcasm.
Definitely remember that.
Now look,
I
notice
actually like
something.
this.
Notice we've got 3 factors. What's our degree? 3. We already knew that, right? This is going to factor into 3 factors completely, okay? Now at this point, because we factored it completely, we just set each factor equal to 0. Okay, so x plus 3 equals 0, x equals negative 3. X minus 1 equals 0, x equals 1. X plus 1 equals 0, x equals negative 1. Okay, and you subtract the 3, add the 1, add the 1. Here are our 3 zeros. We found them. Yay, the crowd goes wild. Okay. Now look, it is not, I'm slowing down right here. It is not a coincidence that our degree is 3. We have 3 factors and we have 3 solutions. Not a coincidence at all. Okay. Your degree, your number of factors that include just an x. Okay. Degree, number of factors that just include x, or include an x, I should say. And the number of solutions will always be the same. Now you might have repeated solutions, so it doesn't look like that, but they will always be the same. Okay. Questions before I do another example of this? This is cool stuff. We're getting to the cool stuff. I know you're rolling your eyes behind the screen. Doesn't bother me. I am a parent of teenagers. I enjoy it. I soak in it, actually. Okay. Okay. So let's look at another one. Let's say we had, and I'm stealing this one straight from the book. Okay. F of x equals negative x to the 4th plus 4x cubed minus 4x squared. Oh crap, I forgot to mention something that's really important. Ugh, and it's something this book does that I just dislike wholeheartedly. Okay, so if you want to go back to where you wrote this down, I've got to mention one more thing, and I'm telling you, it's very particular to this book. Your book uses the word zeros, roots, and solutions interchangeably. Okay, so when you see the word zero, root, or solution, it means the same thing. And Dr. Blitzer, with his book he dedicated to his horse, just that's something he does. Okay. But let's look at this one. So f of x equals negative x to the 4th plus 4x cubed minus 4x squared. Now, first off, just to do what we were talking about before in behavior, this one's already written in descending order, which is nice. We've got a negative leading coefficient, so I know that this is going down and to the right, and we've got an even degree, so it's going to go down and to the left. Okay. So for Dr. Blitzer's sake, let's say find the solutions of f. Okay, it means the same thing, find the zeros. And we're going to do it the same way. We're going to set this whole thing equal to 0. okay? And now I've got to think about solving by factoring, because that's what we're going to do in these first few. Actually, in 3.2, you're just solving by factoring. We don't introduce any fun stuff till later. But if I'm going to solve by factoring, you have to remember the very first rule or very first step is to see if there's a GCF. And if you notice in each one of these, we have an x squared, right? And that first term's negative. If we're going to factor this, we really need the first term to be positive. So I'm going to factor out a negative, and they all have at least an x squared. So I'm factoring out a negative x squared here. And when I do that, that first term becomes just x squared, right? X squared times x squared gives me x to the fourth. Negative positive gives me the negative. This is going to turn to positive, or negative 4, I should say. Take out 2 x's, I'm left with just an x. And lastly, when I take out the negative, this becomes a positive 4. I took out both x's. So we wind up with x squared minus 4x. Oh, shoot. Plus 4. Now I'm going to factor this completely, okay? So negative x squared. Well, this was the easy factoring, right? So let's see, 2 times 2, negative 2 times negative 2, right? Multiplies to give me 4, adds to give me negative 2. Okay, so think about if I wrote this out completely, why not? I'm going to do that. We had negative x times x minus 2 times x minus 2, right? If I wrote it out completely, it would look like this. And notice how many x's I have. 1, 2, 3, 4. 4-3 polynomial, okay? I have 4 factors that include just an x, okay? Now I'm going to solve it, though. So if you solve it, you set each one of these equal to 0. So this is x equals 0. Now look, you don't have to box it in twice, but I'm going to show you that we only wind up with 2 distinct solutions, but these 2 repeat themselves, okay? They repeat themselves, which is kind of interesting because something happens when you repeat yourself. I'm actually going to graph this one. But so we have the 0 repeats itself and the 2 repeats itself. So we still have 4 solutions here, okay? We still have 4 solutions. It's just that the 0 and the 2 repeated themselves twice. I'm going to graph this to show you what's going on. Okay, so we know the x-intercepts are actually at 0 and at positive 2. Because remember, the solutions and the zeros, if they're real, they're really just the x-intercepts, okay? They're at 0 and they're at positive 2. Now, I know the end behavior is down and down. So what that means is, like, let's say this leftmost 0 here. I know that from this leftmost 0, we have to go down here, right? Now, I really want you to think about this. If we went up and my end behavior was down and to the left, so if we went up here, eventually we would have to come back down, which would create another x-intercept. But we don't have another x-intercept. We know the only 2 x-intercepts are 0 and 2, okay? So from here, from this intercept, we go down. And from the right intercept, the end behavior is down. So we know that we go down here too, okay? Kind of neat. Now something crazy happens here. What happens is if your solutions repeat once, so there's 2 of the same solutions, they bounce off the x-intercept. So this makes like an M shape. Okay, it makes an M shape because it actually bounces off the 2 and it bounces off the 0. We're going to talk about that more in a minute. We're going to give it a name, but it's kind of interesting. This is what this graph looks like. And notice we have 2x value. It looks like we only have 2 solutions because there's 2 x-intercepts, but really they repeated. Okay, really they repeated. Questions about this one? So I'm going to go back to that previous one now. we found all that information from it, the one we did down here, and I'm going to do the same thing. I'm going to make a rough sketch, okay, from what we know. I'm going to make a rough sketch. Not a perfect one, just from what we know. I know that my x-intercepts are -3, 1, and -1, okay? So I've got -3, -1, and +1. I know my x's go through there. Now look, remember from the last section, if we want to find the y-intercept, it's just the constant. If we have a constant, that means that's my y-intercept. The one we just did didn't have a constant. Okay, so it was actually 0. Now here's what we know. Remember the end behavior is down and to the left and up and to the right. So my leftmost 0, I have to go down here, okay? And my rightmost 0, I've got to go up here. Because I know it ends down and to the left and it ends up and to the right. But now look, none of these repeat. Do you see that? -3 doesn't happen twice, 1 doesn't happen twice, -1 doesn't happen twice. And when they don't repeat, it means that our graph goes through those intercepts. So it goes through them, goes through down here, and it goes back through up here. So it looks something like this. The graph of this line looks something like this. It's not perfect, okay? It's not perfect by any means, but it looks something like that. Okay, questions? Comments, concerns? So I'm going to do one now that's factored for us, and oh my gosh, it is pretty dang easy, okay? It turns out these are a little easier to graph if they're factored already. Okay, so if we've got, let's call this one g of x. We've got g of x, and we've got, let's say, -2, x minus 3, x plus 2, and x, let's say, -1 squared. Okay, so we've got this one that's already factored, and it turns out to be a lot easier to graph. Now look, I'm going to do the end behavior again because we needed to graph it. Okay, I'm going to do the end behavior again because we need to graph it. Okay, end behavior, remember this x here happens twice, right? So my leading term, I'm going to kind of go about it that way. My leading term is going to be -2 x, right? So x to the 4th. I've got 4 x's going on. 1x here, 1x here, and then 2 x's here. So -2x to the 4th. So that means I'm going to go down because the leading coefficient's negative. It's even, so the other one's going to go down as well. Okay, the other side is going down as well. Okay, that's old stuff, right? But now I've got to, I'm going to say, find the roots. It's the same thing as the solutions, which is the same thing as the zeros, okay? Now, I'm going to think of this, though, as factored out. So it will be -2 times x minus 3, x plus 2, x minus 1, x minus 1 equals 0. Now, what's nice about it being in factored form already, I don't have to do all that work, right? I don't have to factor by grouping. I don't have to factor the trinomial. This is already completely factored. I don't have to worry about that -2 because it doesn't have an x value, okay? So I'm going to set each one of these equal to 0. Oop, x minus 1 equals 0, minus 1 equals 0. So we wind up with x equals 3, right? Because x minus 3 equals 0, x has got to be 3. X equals -2. X equals a +1, and that happens twice, right? And again, check it out. The degree's 4. We've got really 4 factors that include an x, right? And 4 solutions. Not a coincidence. Okay? So now I'm going to graph this. Oh, with the really, let's try to get a straighter line here. It's not that great, but it'll do. Okay. I've got to, I got to graph my intercepts. So I don't know my y-intercept. Actually, if you want to find the y-intercept, you multiply the constants together, -2, -3, 2, and -1 twice. I'm not worried about it. Because we're just going to do a rough sketch of what we know. We know that our line crosses at 3, it crosses at -2, and it crosses at positive. Well, actually, it's not going to cross at +1 because we have 2 of them. Remember, if we have 2 of them, it's going to bounce. Okay, I'm going to make the formal definition of that here in a little bit. But for now, we're just going to say it bounces. Okay, now the end behavior, though, is down and down, right? So that means my furthest left solution, or x-intercept, goes down. It goes down. My graph's going to go down and to the left. And my furthest right, same exact thing. It's going to go down, right? Okay, but look, the +1 here, we're going to bounce. But these outside 2, they only happen once. So we're going to go through, because 3 only happens once, or -2, I'm sorry, only happens once. I'm going to go through that. I'm going to come back down. But look, 1 happens twice, so I don't go through here. I'm going to bounce. We have another M type function, okay? Look, the graph of this does not look exactly like this. This is a rough sketch. We know that it goes through -2 and positive. Oh my gosh, did I graph this wrong? No, it goes through -2 and +3, right? But it bounces at +1. So it looks something like this. And my end behavior is correct, right? Down and to the left, down and to the right. Okay. Kind of neat, kind of nifty. Okay, questions? Those are 3 really good examples from today's lecture. I'm going to give you an example like this one, and I want you to try it, okay? I might steal it from the book if I can see a good. Oh, that's 3.2. Oh, I'm in 3.2. What am I saying? Let's see if I can find one that I like. Okay, yeah, this is like 26 on page 361. So 26, f of x equals 3 times x plus 5 times x plus 2 squared. Now it says find the zeros and give the multiplicity. Now the multiplicity is the number of times the solution occurs. So like for this example, the multiplicity for the 3 and the -2 is just 1. We use a capital M for multiplicity. The multiplicity for these 2 is 1. Now the multiplicity for 1, though, would be 2 because it happened twice. Okay, that's just the multiplicity. So state whether the graph crosses the x-axis or touches. That means it bounces or crosses. And I want you to make a quick sketch of this. Doesn't have to be perfect, just a quick sketch. So I'm going to change this up actually. I want end behavior, and then I want the zeros, and then I want a quick graph. Okay, I'll put the graph over here. I want those 3 things, what we've been doing a second ago, okay? And I'll go over multiplicity again. You don't have to worry about that. So end behavior, the zeros of the function, and then I want you to make a quick sketch, just where it crosses the x-axis, and if it bounces or if it goes through. Draw that on your graph. I'll give you a few minutes. I need to get some water. Okay, let's see. See if we can work this one. In behavior, okay. Well, we've got 3x, x, and x, right? So really we have 3x cubed. So the in behavior here is going to be opposite, right? Positive, so we're going to go up and to the right, but then it's odd, so we're going to go down and to the left. So up and to the right, down to the left. Now zeros, though, which is kind of nice. Look, 3 doesn't matter. So if we want to write it out, so our brains kind of see it, not a dang thing wrong with that, okay? This doesn't have an x, so it's not going to change. It's not a variable, right? So x plus 5 equals 0, so x equals -5. X plus 2, look, I'm only going to write it once because I'm going to be a little lazy. Efficient in mathematics, right? We're going to be efficient. Look, x equals -5, and x equals -2. Now, the multiplicities, though, -5 only occurred once. This -2 occurred twice. It comes from 2 factors. So therefore, the multiplicity is 2, okay? And what that means is we're going to bounce here, and we're going to go through here, okay? We're going to go through here. So let's graph this. Okay, -5 and 2, so I can kind of graph it to the left. 1, 2, 3, 4, 5. So at -5, we're here. At -2, we're here. And we know the in behavior tells us it's going to go down and to the left here, and then up and to the right here, right? Because those are the only 2 times it crosses the x-axis. Now, one of these bounces, though, the -2 does. So what happens is actually we bounce here at the -2 and we go through at the 5. So something, now look, this is not perfect. This is just a rough sketch of what's going on. Okay. Very, very rough sketch of what's going on. Okay. Questions, comments, or concerns? Okay, great. Yeah. Let's just talk more formally about multiplicity. It turns out the rule for multiplicity. Multiplicity. It's not. I don't think I spelled it right. Lord, I did not spell it. Multiplicity. Maybe an I in there. It's not just a really corny 90s movie with Michael Keaton. First off, in this chat box, give me a yes if you have seen the 1990s movie with Michael Keaton titled Multiplicity, because I've used this reference now for like 10 years, and I'll tell you, less and less people have seen this movie. Hey, Jesse's in. It's not, if you, I don't even know, it might be on Netflix or something. It was about cloning, and it was just goofy. I think it was a rom-com. It's been so long. Okay, anyway, but multiplicity here. Multiplicity really talks about multiple factors. Okay, if we have an even number of factors, the solution even number of factors, the solutions from the factors will cause the graph to bounce at the x-intercept. Okay, that is horrible English. Please do not contact Dr. Baird or Mr. and Miss Thomas or Miss Cisco or Miss Noblin on me, okay? But this is what we've been doing so far. If there's an even number of factors, we're bouncing, okay? Even number of factors, we're bouncing. If there's an odd number, we go through. Odd number of factors, the x-intercept, God, English. This is horrible English. The graph goes through the x-intercept. I can tell this is after an hour of talking, okay? An odd number, we go through, okay? That's all we really need. I apologize for this grammar. And it's what we've been doing so far. So like if we look back at this example, this is horrible English, guys, but if we look back at this example, notice we have one factor here, here of x plus 5, and we have two factors of x plus 2. Because, that's fine, Lauren, I'll see you. Because x plus 5 happens once, we're going to go through the x-intercept that's created by it. X plus 2, since it happens twice, it's going to bounce where the x-intercept is created by that solution. Okay, that's all that's saying. We've already done it. I just feel like I had to kind of define it horribly for you today. And I want to quickly get this off the screen before it looks even worse sitting there longer. Okay. That's it for this homework. So, say it again.
I already took a picture of it for Miss Thomas.
Oh yeah, please do that. Now for homework though, and I'm going to tell you, we haven't seen all of the homework. I need you to work it. I need you to come with me with questions next class period to see what you kind of know or don't know, because everything's going to build on it. Now tomorrow's its own kind of thing. I say tomorrow, the next lecture is its own kind of thing. But then after that, in 3.4, we're really going to solve these very, like in a very in-depth way of solving. But for homework, I want you to do 15 through 31, and then skip over. I didn't talk about intermediate value theorem. It's not that important. 41 through 63. Okay. And then skip over. I want you to do a few real world examples. There's 73, 75. Yeah, 73. So homework. Now this starts on page 360. And it's section 3.2. Okay. 15 through 31, and then 41. Now all of this is odd, guys. Odd. Do all the odds. Okay, so check that out, get that done, get back, try, do the homework. If it doesn't make sense, let me know. I'll go over it in the next class period. Actually, we could spend the next half of the next class period just talking about this section. Okay, I feel like it's one of the kind of the capstone. This is the capstone chapter, in my opinion, of college algebra. Okay, any questions before I get off here? I've got to leave a few minutes early because of a meeting. But we've done everything on here.
Everybody have a good weekend.
Yeah, everybody have a great weekend. I'll see you all on Monday. Bye, guys.